Lesson 105, Paul explained the operation of NeoPixel smart LED devices. Some NeoPixel devices, such as the strip in the SunFounder kit, have 3 leads, 2 for power and 1 for data in. Many devices have a 4th lead, data out, which is used to daisy chain devices together by feeding the data out of one device to the data in of the next device. Each individual pixel on a device has 4 leads, 2 for power, 1 for data in, and 1 for data out, which feeds the data in pin on the next pixel on the device. The last data out pin is available to feed data in on the next NeoPixel device. The color of each pixel is defined by a 24-bit data word. Each pixel decodes the 24-bit word into a single color and passes any remaining data to the next pixel. You are probably familiar with representing colors with RGB or HSV data. These systems represent each color with a tuple. For example, a color could be represented in the RGB system as shown here. As an example, we'll encode the RGB tuple 255, 75, 128 into a 24-bit word. We start by converting the red component to a 24-bit binary number. We shift the red bits 8 bits to the left. We repeat the above process for the green component, shifting the green bits 16 bits to the left. We convert the blue component to binary but do not shift the blue bits. Finally, we OR the shifted red and green bits with the blue bits. This produces the 24-bit word for 1 NeoPixel. So the RGB color 255, 75, 128 can be represented on the NeoPixel using the 24-bit word shown here. We'll soon see that this is all relatively easy to do in MicroPython. The NeoPixel spec sheet tells us that we cannot simply send the 1s and 0s of the 24-bit word to the data in pin. We have to encode the 1s and 0s in a very specific way first. Each 0 in the word must be represented by the low-high-low pattern shown below. A T0H pulse width of 375 nanoseconds and a T0L pulse width of 875 nanoseconds would meet the NeoPixel requirements. An 8 megahertz frequency gives us 125 nanoseconds period for each executable state machine statement. So holding data in high for 3 clock cycles and low for 7 clock cycles should signify a 0. In a similar way, each 1 in the 24-bit word must be represented by the pattern shown below. A T1H pulse width of 750 nanoseconds and a T1L pulse width of 625 nanoseconds would meet the NeoPixel requirements. At 8 megahertz, holding data in high for 6 cycles and low for 5 cycles should signify a 1. Paul gave us our assignment in the middle of lesson 105, asking that we create a state machine program that would encode 24-bit words coming from Python and drive the data in line accordingly. Paul suggested that we try it a little while, then come back to watch his solution. I tried it a little while, all right. I struggled with the pull statement for quite some time. I finally had to admit that I could not pull the 24-bit word into the state machine in a useful way. The clouds parted somewhat, though, when I discovered the auto pull statement. When you set auto pull to true and set pull thresh to a value of 24, data in the TX FIFO will automatically be pulled into the OSR whenever the amount of data in the TX FIFO reaches 24 bits. Given that, I expected to put each of our data words into the TX FIFO 24 bits at a time, but that doesn't seem to work. Instead, you have to put each data word 8 bits at a time. Is it possible that the NeoPixel needs some time between dealing with each 8-bit packet? I don't know. Please leave a comment below if you can shed any light on this. Let's have a look at the code. Our program starts with imports as usual. We import pin because we'll be using the pin statement, RP2 because we're creating a state machine program, and time because we're going to use the sleep function. Next we create color array, an array of RGB tuples. These colors were sampled approximately every 30 degrees around the edge of the HSV cone. Here we declare the GPIO pin where the NeoPixel data inline is connected. We also declare the total number of pixels that we want to control. The addRP2 statement sets the initial state of our output to low and the shift direction to left. It also sets auto pull to true with a pull threshold of 24 bits. I was surprised to learn that state machine programs could include variables. They don't seem to count against our 32-line limit, and they make the program much easier to read. Our program starts by declaring the 4 cycle times that we selected earlier. Here we copy null to the X register to remove any prior data. Then we shift the most significant bit out of the OSR into the X register. Remember that the OSR is refilled automatically because auto pull is set to true. If the bit we move to X is 0, we jump to the It's 0 label. Otherwise, if the bit in X is 1, execution falls through to the It's 1 label. This is where we encode a 1. We set pin 0, that takes a clock cycle, then delay for T1H minus 1 clock cycles. So pin 0 is high for T1H cycles. Next we reset pin 0. That takes a clock cycle. Then delay for T1L minus 1 clock cycles. So pin 0 is low for T1L cycles. Then we jump back to shift in and get another bit from the OSR. If the bit in X is 0, we arrive here at the It's 0 label. This is where we encode a 0. We set pin 0, that takes 1 clock cycle, then delay for T0H minus 1 clock cycles. So pin 0 is high for T0H cycles. Next we reset pin 0. That takes a clock cycle, then delay for T0L minus 1 clock cycles. So pin 0 is low for T0L cycles. Then we jump back to shift in and get another bit from the OSR. Here we instantiate the state machine, specifying that it will be state machine number 1. It'll use the My NeoPixel code. It'll operate at 8 MHz and use a NeoPixel pin as its output. And here we activate state machine 1. A try except structure follows. The try clause contains a while true loop and a for loop, which encode the RGB data for successive elements of color array into a 24-bit word for each connected NeoPixel. The starting color increments before each pass, giving the appearance of a running rainbow. After a brief sleep, it all happens again. There's a lot going on in the statement on line 52. The less than 8 directive performs the binary shift left by 8 bits operation on the red component of the selected color. The less than 16 directive performs the binary shift left by 16 bits operation on the green component of the selected color. The vertical bar symbol is the symbol for logical OR. We OR the shifted red and green bits with the blue bits. The result of this manipulation is the 24-bit data word for the selected color. Line 52 finishes by putting that number in the TX FIFO of state machine 1. The (8) means that the transfer is done 8 bits at a time. The except clause uses a for loop to put 0 into each connected NeoPixel, turning it off. After a brief sleep, the state machine is deactivated and the user is advised that the program is finished. And here's how it works. The Pico is connected to a 12-position NeoPixel. A 24-position NeoPixel is fed by the data out of the smaller device. I reduced the exposure and blurred the focus to try to make this easier to watch. I watched the remainder of lesson 105 after I finally got this assignment working. Now I have more questions. I learned about side set, but didn't need it. I learned that Paul had to split the 0, but I never encountered that problem. I'm still hoping someone can explain why the put command finishes with "8" instead of "24. If pull thresh is 24, why can't I put 24 bits? Any and all comments are welcome. I replaced my state machine code with Paul's code. Both programs seem to work equally well. I'm going to call this assignment complete. Well, that's it for this assignment. Any and all comments are welcome. Don't forget to like or dislike the video before you go. And feel free to subscribe. Don't forget the notification bell. We'll talk to you next time.